Thank you all for coming. I don't recognize any of you, nor can I recall why I'm here. Now, without further ado, welcome to Docker from Scratch. My name is Aaron Powell. You'll find me on the internet at various locations that are displayed on the screen. And I'm from Australia, if the accent hasn't given that away yet. And I work for a consultancy company back in Australia. And a couple of years ago, we were finding that a lot of our clients were wanting to understand Docker. They wanted to work out how it could be used. But when we were trying to understand it ourselves to be able to help them, what we were finding is that people were talking about all kinds of things, immutable infrastructure, how you do containerized applications, microservices, blue-green deployments where you're hot swapping containers that are running in a Kubernetes cluster in AKS or ACI or whatever the orchestrator might be on whatever cloud platform it is, and you're trying to replicate your dev environment exactly in production, and all this stuff was like, that's everything that they were talking about. That is not what this talk is about. We are going to start from the basics, because what we found was that it was great to learn all this stuff about how you could use microservices in these Kubernetes pods that could scale out to as big as you could ever possibly need. But if you didn't understand the basics, and there really wasn't a whole lot that we could find that was going to help people understand the basics. So that's what this talk is about. We're going to be starting from scratch. And that's a little joke that I've got in there that hopefully you'll also find funny by the end of the talk. If not, I will just try and move on. So if you're looking for something a bit more advanced than that, feel free to wander off to one of the other sessions. I will not be offended. Just leave a green slip in the front because I did warn you that this is going to be an introduction talk. But before we get started, I want to talk about some useful terminology to know when we're talking about Docker. Docker is not a virtual machine. And this is a common misconception that people have, particularly when they're first coming to Docker, is, oh, it's basically just a VM. Particularly if you're running it on Windows and you're trying to run Linux containers, you're running it in a VM, so it's just a VM, right? Well, it's not really. It's actually, it's grown out of Linux. So we do have Windows containers now. They're slightly different. Conceptually, they solve the same sorts of problems, but architecturally and the way they're implemented is very different because of the differences between the Windows and the Linux kernel. But in Linux, it really grows from the things you can do with inside of the kernel just natively, using like chroot, namespaces, C groups, and stuff like that. It's really about having user space isolation of processes. That's ultimately what Docker is about, and that's what the container is a process isolation. So when you're working with Docker, kind of any container engine runtime, we have images. Images are our starting point. This is what we will build. It's what we share with other developers on the team. It's what we push to different environments, roll to production, etc. But that is our base starting point, is an image. From an image, we run a container. So a container is actually just a running instance of an image. I still, every now and then, will accidentally say container when I mean image and vice versa. So I apologize if I make that kind of wording mistake, but they are very different. Like I said, a container is run from an image. An image is just something that lives on a hard drive, essentially, or in a repository somewhere. And then finally, we have a host. The host is the thing that's going to be running the containers and the images are stored within. So my Windows 10 laptop here is a host for Windows containers and Linux containers. Well, the Linux containers are technically running inside of a Linux virtual machine, either in Hyper-V or in Moby Linux running inside of Hyper-V. If you're running on Linux, you can use the native Linux install as the host. If we're talking about Azure or GCP or AWS, then the host is whatever that cloud platform is providing. So this is a pretty typical Docker CLI command. We start with the Docker CLI tool, Docker, unsurprisingly. We then give it a command that we want to execute, run images, et cetera, We'll see some of these commands throughout the rest of this talk. We then provide it with some options of things that need to go into that command that we're going to be running. So I'm providing two options in this case, -it, which is telling it to be an interactive container that we're starting up, and --rm, which will tell the container to clean itself up when it's stopped. We'll see that in action shortly. We then provide some arguments to it. to run a container, I need to tell it the image. So that's that first bit there. That's Ubuntu. I'm telling it I want to run the Ubuntu image. And then what command do I want to execute when that container is started up? I'm going to execute bin bash. All right, and that's basically it for my slides. I figured that standing here and doing a slide deck for an hour is going to be fairly uninteresting, particularly from a Docker introduction talk. Instead, I'm going to jump over to the command line. So I've got just a standard prompt here. I'm using WSL on Windows, but this could be done from PowerShell. If you're using a Windows machine, you can probably do it from cmd.exe, but no one should do that. If you're on Linux, your shell flavor of choice. And I have a line of code here that is actually what we basically just saw on that slide. So I'm using docker run dash IT because I want an interactive container, something that I can connect into. I'm telling you the platform I want to run is Linux. This is needed for if you're using Windows, because Windows can run both Linux and Windows containers simultaneously. You need to tell which operating system platform you want to execute on. By default, Windows will use a Windows container. Unfortunately, there is no Windows Ubuntu container, image. So that will fall over there. I told you I was probably going to use image and container interchangeably by accident. So we try and run Ubuntu on Windows, and it would fail because that doesn't exist. So we tell it it's Linux. So we're going to run a command. So let's execute that and see what happens. Cool, so now my prompt's changed because I'm now connected into this running Ubuntu instance. And this is Linux. It's a container that is running a flavor of Linux, in this case the Ubuntu flavor. I can ls, I can see a file system, I have it /root. I can run bash commands like in $ls do echo $a and done. So that's just like really obviously primitive shell scripting there. I've just done a for loop over that's iterated over each of the directories as a result of ls against the root file system. So it's Linux for all intent and purpose. If I exit that container, shut down, and now I can use the Docker CLI, a different command, ps, which displays running Docker containers. I have no container running because I exited that. But if I was to change that, give it an option of -a, now I can see all the containers that are running, all containers that have stopped or have failed to start. So you'll see that one there, Ubuntu, the command that executed was bin bash. It was created a minute ago. It exited 16 seconds ago. It's got a container ID and a name. So why did it stop when I hit exit, when I typed exit? Well, the reason for that is that a container in Docker will be running a single process, and that container will keep running until that process terminates. So we told it to execute bin bash. I could have done bin sh, or I could have done a variety of other binaries or executables inside of there. And once that process stops, the container stops. But it's still there, so I could do docker start, and then we give it the container ID. I can just give it an abbreviation of the container ID. So I just give it 22, and then that starts. So if we do docker ps, we'll see that it's running again. It started up 5 seconds ago. So now I could do docker attach to 22. I'm just going to split my terminal. Wait for my other terminal to come up. So you'll see I'm back in at that prompt. And then if I was to do docker logs, so a different command that I execute, so this allows me to follow the standard out logging of the running container. I'll give it 22. And let's jump back here. And if we do ls, you can see that the logs, I'm getting all the information that's happening within inside of that container. So that's how I could observe what's happening on a container that I might not actually be attached to. Now, let's go back and kill that. And then if we do docker stop, so I can issue commands at the container. So I can say docker stop. I want to stop a particular running container, stop 22. That will send the appropriate sig term to it, and that will turn that will end that process within inside that container, doing graceful exiting. I can do docker kill if I just want to just terminate that process directly. But obviously, you probably if you're wanting to stop a container, you're wanting it to do a nice shutdown. Maybe not for running bash, but something a little bit more advanced you might want a proper shutdown for. Let's just clean up my terminals, and Then the last thing I might want to do, I want to like completely clean up what I had running, so I can do docker rm, which is remove, and then remove what particular container. I can provide it the container ID, or I can provide it the container name. It had a kind of a funny name. If we just go back to ps-a, it's got a funny name of Zealous Pike. I could give it that name, or I could give it the container ID. I basically just have to give it something unique to know how to terminate it. So docker rm22. Now if we ps-a, we have no running containers. Another useful command, docker images. This shows me all the images that I've got on my machine. So these are all the ones that I can start. Obviously, I can pull down new images from a container registry. That could be Docker Hub, which is the open source container registry. You could have your own private container registry inside of AWS, inside of Azure, inside of Google Cloud. You could host one yourself, wherever, whatever it might be, and you can pull those down. But these are just containers that I've got on my machine. All right, so let's go to the next demo. I can run multiple containers from the same image. So here, what I'm doing is I'm starting 3 different containers. I'm giving it a different argument that I didn't have on the previous one, which is the -d argument here. -d says start this container detached. It's still an interactive container. I can still attach to it, but you're not going to immediately bind my console to it. So I won't have an immediately access to that container. And --rm, I say, it will clean up that container when it stops. So let's just run that. And I'm going to create a couple of shells. All right, so while they all start up, if we do docker ps, see that we now have 3 different ones here. Oh, actually, the other thing that I did with this one, I provided it with a --name argument. This allows me to control the name rather than that automatically generated one. So like the Zealous Pike, which it generated for me. I might want to have a bit more control over that, something that I can then use. It's friendly, I know what it is. So in this case, I've just called it Ubuntu 1 through 3. So now I can go docker attach to Ubuntu 1, and then down here, attach to Ubuntu 2, and docker attach Ubuntu 3. Okay, so these are all independent of each other. They do obviously look the same at the file system because they've all started from the same image. So they all started their life identical. But let's take Ubuntu 2 here, and if I do echo hello NDC Oslo, and just redirect that out to foo.txt. Oops, and if I could spell echo, that would help. Echo, there we go. Now if I see, I have that file that I've obviously just created there, but if I was to come up to any of the other ones, oops, wrong one, you'll see that the only Ubuntu 2 has that file within inside of its file system. That's because each of these containers is completely isolated from the others. It doesn't have access to the files in it, so I can create files in one that no one else has access to. They're fully process isolated. I could do, say, a docker stop on Ubuntu 3, and you'll see that it's done, it sent the sig term to that one down there of exit. That process has terminated, the bash process has terminated, and that container has shut down. So I'm now back at my WSL prompt, and if I docker ps-a, I only see Ubuntu 2 and 1 running because I terminated Ubuntu 3. And the --rm meant that it was going to automatically remove itself once the process is completed. So I can easily then get rid of all of them. If I want to do, if I do docker ps-q, I get just the process IDs. I could then pipe that through to the xargs command in Linux, which just takes the output of one process, turns it into arguments so I can pipe to another process, and then docker stop. And you'll see that sent exit to both of the others. Now all 3 of them are done, closed, and we have no more running or stopped containers on my machine. And time to clean up all of our terminals. All right, so let's go. I've got 14 live demos, so I'm really hoping that the demo gods are kind to me today, and you're going to see a lot of Git checkout. So, on to our next one. When people talk about what they can do with containers, they obviously talk about running microservices in production or containerizing legacy applications so that you can have simpler deployments and stuff like that. But I actually think that there's a big opportunity people don't realize that you can do with containers, and that is what I refer to as single-use containers. So let's say that I've got something that I need to, I've got an executable I need to run, but I don't actually have that on my machine. And when I first came across this, realized that I could do this was I was doing technical interviews for the company that I work for, and we have our candidates submit a code puzzle that we review and talk to them about during the interviewing process. But this one candidate had sent their puzzle or their solution as a .rar file. This is in 2016. I haven't paid for WinRAR license for ever. I don't have WinRAR on my machine. I don't have 7-zip on my machine. My machine is completely transient. If it dies, I pave it and start again. I don't install software I don't need to install. And who's using something other than zip or as an archiving format to just share things around, or at least as a bundling format? I just couldn't wrap my head around why would someone be using RAR. And I was like, well, I mean, I need to unpack these files, right? Because I need to review it to talk to the candidate about it. But as soon as I install 7-zip or WinRAR, I know that's putting stuff in the Windows registry. I know it's putting stuff in random locations all over the Windows file system. And it's just, even if I uninstall immediately after, I could use Chocolatey or something like that to install and uninstall. But it's still going to leave things that I don't really want left on my machine. No matter how good you think the uninstaller is, it's always going to leave something behind. So, like a good software engineer, I decided to work out how I could best over-engineer the solution to the problem that I needed, and that was to go find a Docker image that already had Unrar inside of it. Found one on Docker Registry, and I decided, well, I'm just going to pull that down. It's going to do exactly what I need. So I found this one. It's by some person, but it's inside of it. It's got Unrar. That's all I need. And I know that this is going to clean up nicely on my machine afterwards, because when I remove that, or when that container stops, I can have it auto-remove, or I can remove it myself, and then I can remove that image, and all traces of Unrar is gone from my machine. So, let me just clean up from when I last ran this to show you what the output would look like. So this command, but this does also introduce another thing. I showed you in that last set of demos that the file systems are unique per container that's running. If I create something in one, it's not available to the others. But I need to get something off my laptop into the file system of this running container. And we can do that with volumes. So I have a -v, about middle of that command there. -v, or /volume, if you want the long version of it. Then we provided a path on my local file system, and then :, and then the path on the containers file system that I want to mount. So what this will create is essentially a mount point between your file system and the container. Container can then access files that are inside of that folder, and only that folder that you've specifically mounted as a volume. It can't access the rest of your file system. And then it can be mounted in a read-only mode, or it can be mounted in a read-write. By default, it does a read-write, which is what I obviously need for this, because I need to unrar some files. And then I'm telling it I want to execute the unrar command. That itself takes some arguments and ultimately has to take the file I want to unrar. So, how does that look? Well, it's doing exactly what it shouldn't have done, which is fail. Awesome. There's nothing like the present for having demo fails happen. Let's just try one more delete of that. Make sure it has, well, you'd think that when I went right-click delete on that, it would actually delete it, but apparently not. So let's just try again. And thank you, something is locking that on my file system, and this is going to be a really terrible demo if I can't actually delete the files I need to delete. Well, let's give it one last crack, and then I will just move on to the next demo. Okay, so I've got something that's locking something on my file system, but you can kind of see the idea. Like, Unruh has started up. It has obviously detected there's something on my file system that it can't write over the top of, so it's just then bailed out. Hopefully you get the idea, and I don't get too much sympathy from the fact that my demos are failing already, and we're only at number 3. There's only 11 more of these to go. I can math. It's a little too early in the morning. Okay, so let's go to the next demo. All right, so the idea of running single processes inside of containers, that's highly useful, and it allows you to also do a bunch of prototyping of stuff that maybe you don't want to install things on your machine. I wanted to dabble with Golang. I'm not sure if I want to become a Golang developer, and I don't quite understand how the Go ecosystem works like that, and I don't want to do something that's going to mess up my Windows file system as I'm trying to futz around and get Go installed, or Python 3 or 2, and then you got to install both because something's working one, not the other, or all this kind of stuff. Well, I can pull down an image that has all that set up inside of it, and I can work with inside of that image, and then when I'm done, I can either destroy it and get rid of it and blow away the container, or I can then choose to actually install things on my bare metal. But I tend to put as much stuff into containers as I possibly could. So this is how you could run Node inside of a container. We just pull down the Node container. I'm pulling down Node. I'm running, again, I've given it a name. This one is Node, but then it's got a colon after it. And then 7.7.4-Alpine. So when you create an image and you push it to a registry, it's got 2 bits of information. It's got the image name, in this case Node, and then it's got the image tag, which is in this case 774-Alpine. Tags are really useful because they allow you to have the same image name, but different flavors of that. In this case, 774 is the version number of Node that's going to be running with inside of that container. And then this is instead of using Ubuntu as the base OS, for lack of a better descriptor, it's going to be using a flavor of Linux called Alpine, which is much smaller and much better designed for production. So how does that look? Just before we run this, Docker images, you'll see that I have both the Node ones here, Alpine and just 774 raw. And you'll see that there's a bit of a size difference between them. 666 meg versus 59.2 meg. So you probably only, the larger one might be more useful if you're doing local development. It's got more debugging stuff built into it. But in production, you probably don't need all of that. You probably don't need this really large image that's being spun up, because that's obviously going to consume more memory when the container is running and stuff like that. So you might use a different flavor, a more slimmed down, specialized, designed for production sort of image. So let's execute this, and now I'm in a Node.js command prompt because I'm executing the Node binary with inside of a container. So I can do console log, hello, NDC Oslo. It's just Node. I could get the file system via require, and we could do fs reader of slash, and then paths, and console.log paths. So I've still got access to, it's just Node. The same as if you were installing Node on bare metal. I can run it within inside of a container. I could have pretty much every permutation of Node version-wise that I want. So if I let's say I wanted to test something against the latest the latest Node 10 release, but we weren't sure if we were ready to port our application from Node 8 to Node 10. Well, maybe I could pull down the container. I could run pull down the image, run the application with inside of our container running Node 10, see where errors might be without having to install multiple versions of Node, use like an NVM or something like that to manage them locally. That's one other use for single-use containers. All right, so moving on. What if we actually want to run something with inside of our application. So I want to actually run an application with inside of Node. I've written a very complex Node application. This isn't a Node talk, so if you're not a Node developer, I'm sorry, this code's probably going to be really hard to understand. Waits for the comedic effect. 3, 2, 1, moves on. It's a basic web server bound to port 3000 that we're going to be running with inside of our container. So again, I'm going to do a volume mount. Volume mount the current working directory to /source, set the working directory, which is the -w, to the run command to /src, because that's where my code is now living. Then Node will, the container will start up. It will run the Node binary with app.js as an argument, so it will start my web server. So if we just run that, cool. I've also started this in detached mode, so we can see Docker PS. We'll see that it's running. You can see the command that's executed. It's up. And then if we were to curl HTTP localhost 3000, and oh, it's failed to connect. Don't worry, I actually meant for it to fail. So that was fully expected, because well, I've said it's listening on port 3000, but that's port 3000 on the container's network. But it's not on my network, not on my host network. The host doesn't even know that port binding exists. And we can see this if I do docker inspect, oops, and oops, that's not what it should have been. Where was that container ID? 24. So that command that I've just executed, don't worry if you're not following along with that. You're not necessarily meant to memorize that. But basically, it's a little Go template that iterates through a JSON payload to find a particular section of that. In this case, I'm looking for the ports that are bound on the networks that this container has available to it. And the output of that is blank, because this container has no ports bound to its network. The Node process is bound to a port, but that port is never exposed anywhere within inside of our network. So on to our next demo. If I want to have something that's running on a network that is allowing inbound and outbound requests, I need to explicitly bind those ports. I've added an extra argument to this, -p, double dash port if you want the long name, and I specify a port on my host bound to a port on my container. So in this case, I'm going to bind port 8080 to port 3000. We'll just get that running. Docker. I probably should actually stop that one. So let's just do docker stop 24. Give that a moment. I should have just done a kill. I didn't actually need that to gracefully shut down, but it's going to gracefully shut down anyway and clean up in any minute now. There we go. And let's run this again. Okay, so let's just run that docker inspect command again. And that's going to be on 76. So this time you'll see that I do have an output of that because it knows that I've bound that port. Port 3000 on TCP is bound to the host port of 8080. And if I do a curl of that against localhost, so containers are at least on Windows, pretty sure on Linux as well, implicitly bound to localhost. So I get, from a networking standpoint, you can control the networking a bit more. We'll see that a little bit later. So that's how we can connect to it. The port that you're binding on your local machine doesn't have to match the one on the container as you've seen. And that can be really useful if you've got, say, an application that's running and it just wants to run on port 80 because that's what it runs with inside of its container. But you're actually maybe sitting Nginx in front of it, so you're going to have some redirects happening and or some other port binding. So it might be locally bound to some random port, which then Nginx is doing a port forward through to. So that's our lovely web server. It's, like I said, it was a super complex bit of code. You didn't need to follow along, but that's how we can run a web server with inside of a container. Okay, so let's just stop that one. Should have killed again. So now I got to wait for Node to gracefully shut down. Any minute now. Just as I'm about to take a drink of water, it does gracefully close. Well, that's nice. So let's go to step 7. So far, all we've done is we've been running containers from images that someone else has built. Even with that node one, I was still just running someone else's node image myself, and that's great for just me. But you're probably working with other people, and I mean, the whole point is that you want to be able to push these through to production. After all, so you probably want to make sure that anything that you're doing locally, that you've got some kind of an output that someone else can use. That's one of the points of immutable infrastructure that you can do here, is that the container, or the image that you get it doesn't change, and you just move that through environments and you change the config that's going to it. Maybe you've set some environment variables, and that's how you change a connection string to a database or an API key for a service that it's using inside the application. So to do that, we need to build an image. So I've introduced another command up here, docker build. Docker build is how we build an image, and this is also where we introduce the Docker file. The Docker file is what we use to describe a series of commands we want to execute against containers to build up an image. A Docker file always starts with a from directive, and that's the base image that we're using. Images are always layered upon other images. So we're always building on top of something else that someone has given us. In this case, I'm building on top of the Node 774 Alpine, so from image name. And then providing a bunch of information that we have. So I'm going to expose port 3000. I'm going to create a directory, copy my JavaScript file into that directory in that image, or in the container this image is going to come from. I'm going to set the working directory, and then finally execute a command when that container starts up. So if we run that, we'll see that it's starting to process all of those steps one by one. So from node, and then there's an ID, expose, and then you'll actually notice between this expose, or under this expose, we have running in, and then an ID, and then removing. So the way a Docker build actually works is it will actually start up a container and execute a command with inside of it, stop that container, snapshot it, and then that's what they call a layer to an image. And then we just keep rinse and repeat all the way down. So that goes all the way through. We eventually get to our final one. It cleans up after itself. You can set flags so it doesn't clean after itself, but you end up within this kind of long tail of images that are not particularly useful. And eventually I've started my web server up. So if we do docker ps, you'll see that it's running. You know the command is actually a little bit different here because it's using the cmd directive within inside of the Docker file. So it's executing bin sh with a string of a command to run. In this case, it's executing node app.js with bin sh. We've got our ports bound, et cetera, et cetera. Let's just stop this one for the moment. Stop, stop B8. Because I want to show you another really powerful part about images. So remember I said that images are all built on top of each other. They're layered. What that means is that if I was to, say, reorder stuff, let's say that I actually go, well, you know what? I probably should set the working directory prior to the copy, because then I can just do copy it into dot instead of copy it into source. Now, if we run that, we have a look at this output, you'll see that these first couple, it's actually got, instead of running in, it says using cache. Because what it's realized is that the SHA of that command that's being executed inside of a container to produce the image is exactly the same as another one that I've previously created. It's the exact same as another layer. So I'm actually reusing that. There's no point in creating it again. I know that these are identical. So I actually get a much faster build time because I don't have to execute a whole bunch of stuff that's previously been executed. This is really useful if you're building images that you have to install a bunch of stuff in. Maybe you are doing something that's going to use the ASP.NET Core runtime on Linux. So you're going to have to install that. You don't want to have to install that every single time. It's downloads and stuff that adds time into your build process. So I can reuse that layer from previous. So that's just how kind of how image layering works. Let's just get rid of that change. Git checkout Docker file, and let's just stop that from running. Oops, Docker kill 1. Let's just kill it that time because then it's going to be faster. All right, and we'll check out our next step. All right. All right, so when you start having even a moderately complex environment, you might be running a couple of different containers that need to talk to each other. They have ports bound and so on and so forth, and that can be quite complex. Just command line things that you have to execute. You end up with these really long, shell scripts or batch files or PowerShell scripts or whatever your scripting language of choice is. But there is another way that we can do this, and that's with Docker Compose. Docker Compose, I kind of have a love-hate relationship with it. It's very great at describing what's happening inside of an environment, but I have this hatred of YAML because it's a YAML file. Whitespace significant languages, just something doesn't sit right with me for those. I'm more of a web developer and JavaScript, and I can deal with semicolons, but whitespace significance is a bit more painful. But this is what a Docker Compose file looks like. It's basically the exact same thing that we had when we were doing Docker run and then specifying an image, some arguments, et cetera, et cetera. But in this case, I've got a service that I'm starting up. The image that service is going to use is the node 774 Alpine. I'm specifying some port bindings on that. I'm mounting a volume, which is the current directory, into /source, working directory, et cetera, et cetera, et cetera. And then to execute this, we use Docker Compose instead of just Docker. Docker Compose it's kind of a separate product to Docker itself. With Windows, when you install Docker, you get both Docker and Docker Compose. If you install Docker on Linux, I'm not sure about Mac because I don't actually have a Mac, but at least on Linux, when you install it, you don't get Docker Compose. You have to install that separately. I'm not quite sure why there's that difference between them, but it's just worth noting. So Docker Compose, we specify the compose file that we're going to be using, -f, Docker Compose -YAML. I'm saying that I want to start up this environment. So that's what the up command is. And then I'm going to give this environment a name of node. And then it will do a bunch of stuff to do some prefixes onto them, and we'll see that in a moment. And then finally, I can do Docker Compose RM, and -f, just kind of a force remove. And that's how we can shut down and clean up an environment once we're done with it. So let's get this up and running. So we're creating a container from that. You see it's given it a prefix of the current directory, Docker from scratch, and then the name that I specified, which is node, and then a suffix of 1 because it's the first service that it was starting. And then if we just have a look at our Docker PS, you'll see that we have this container running. It's now just running as plain old Docker. Because the reason for that is Docker Compose is actually just translating that YAML file into the appropriate CLI commands to execute. And now we can do Docker kill of F3. And by killing that stops the compose from running, which will in turn clean it up after itself, and we're all done and dusted. So we can do other things with Docker Compose. What am I up to? I'm up to step 9. So let's say that we wanted to run something to actually build an image out of it. Taking that second node example that I had where we had the Docker file, I can use Docker Compose to also execute a Docker file and then run a service on the base of that. So this time, instead of having to specify the image, working directory, et cetera, I can do all of that in my Docker file. Same Docker file that we saw previously. And this time, the node service that I'm specifying here has a build property on it on line 9. I specify what's the context of the build that you want to execute. It's in the current working directory, /. The Docker file is called Docker file. That's just the convention is that you use Docker file as the name of the Docker file, but you can call the file whatever you want. Call it Fred if you prefer. and then I'm specifying the platform is going to be Linux that this is running on. Interesting side note about Docker Compose is I'm using the version 2.4 of Docker Compose here. Version 3.5, I think, is the latest one. It's at least version 3 is the latest version of Docker Compose. The version 3 of Docker Compose does not support the platform directive, so you can't say that you differentiate between Windows and Linux containers in Docker Compose version 3, but you can in version 2 because versioning is hard. So that's why I'm still using version 2 for this. And then this will run exactly the same as we would expect it. It's running our build. We see that we've used cache for basically the entire thing because I had pretty much all of that previously cached. It's up and running. Then, yep, there's our web server. All very exciting. Docker PS. And we'll see that that's up and running. If I do Docker images, you'll see the Docker from scratch node at the top there. You'll see the Node.js app directly below it, which is the one that we created by just executing the command line Docker build step. Okay, and then let's just kill, what was it? Docker PS, Docker kill of whatever you are. Okay, cool, Compose will shut down, and we'll check out step 10. Now we might want to be using Docker Compose to do something that is just becomes a bit more clunky to do with inside of a command line, and that is working with environment variables. We might have multiple Compose files for different environments. So Compose files can actually be layered on top of each other. And what you'll see here is I'm running a SQL server. Hopefully this will work. I just realized this is still on version 3. Yeah, this will still work. So I want to run the Linux version of Microsoft SQL Server. Now, to run that, I have to provide an environment variable that says I accept the license agreement, and I've got to give it a super strong SA password. Don't copy my password, please. So I can start that up, do some port binding, but I could then have multiple versions of this file that I just change the environment variable. So I have like a different SA password for the different environments, or like it might be generated as the output of a build step, the Docker Compose file. So I don't actually check in my production database SA password to source control, and then publish that on an open public GitHub repo, and all of a sudden my entire my production infrastructure has been owned. But I can run this, and that will take a moment to start up. Linux SQL Server is quite a large container to get up and running. It's about a 1.5 gig download. So I did that prior to coming onto the conference Wi-Fi, because otherwise you'd be sitting here for quite a while. So there we go. It's just getting started, and I'm just going to open up a couple of files in LinkPad. And that one. All right, so, oops, let's just increase some font size. Zoom, my pretties. All right, and let's just refresh my connection up here, because I opened up LinkPad before the container was fully started, so I couldn't actually connect to my SQL server. But there we go. You can probably see this very small up here, behind the magnifier. Come on, magnifier. There we go. So there we go. It's a completely empty SQL server. Master model, MSDB and tempDB, as you would expect on an empty SQL server. So I can then execute this against the right database connection. There we go. Now if we just refresh our SQL server connection, we refresh and realize that something has not worked, and my demos are failing me again. No! The SA password did not match. That is interesting. Try that one more time. That's going to be a real problem if my SA passwords are not matching. Anyway. in the that is a very good point. I am connecting to the. Thank you, audience, because that was going to freak me out, and I was going to have a lot of problems going forward if I couldn't work that one out. But yes, I probably should create the database before I try and create a table in it. Order of execution problems, yeah, we can deal with those. So this is taking a moment. If we come over here, there's nothing interesting in the logs, but you can kind of see what's happening in our log files there. Give it a moment. That is taking a phenomenal amount of time. All right, that's erroring for some reason, but I think you kind of get the point that I should have been able to execute these scripts, but in the essence of time, I'm not going to sit here and try and debug my life's failings. So let's kill that one, and we'll just jump over to our next step, step 11, and yep, terminate that. Okay. So I said that Docker Compose is designed to be used, designed to basically represent what an environment looks like and execute the appropriate Docker CLI commands. So what if we had something that was maybe running multiple multiple containers? I've got a web application here, and it talks to a SQL server. Fairly standard sort of architecture, web and SQL. And this is what the Docker Compose file looks like. It's an ASP.NET Core application that I build. This is actually all generated by the Visual Studio templates, or it was when I gave this talk last time. These templates all seem to have changed massively, and this stuff doesn't work. But this is the general idea of what the Docker Compose stuff looks like. So I have a service called Demo App up the top. It's got a Docker file that's going to execute. And it's going to bind some ports, and it's going to sit in two separate networks, one called Web and one called DB. And then going to start up a SQL server. SQL server has an outbound port. You've got an image. We're specifying some stuff like that. And it's going to live within inside of only the SQL database. But you'll see that on line 24, I'm calling it Demo App _SQL, because that's the name of the container that I want to start up. But within inside of that network, I'm calling it SQL, because I want some way that I can refer to it from my web application. So you'll see here, my connection string just says it's going to connect to a SQL server called SQL on the appropriate port, blah, blah, blah. And that should all be up and running. But you can do that all just from the standard command line steps. So I'm doing a .NET build at the top. Once that's completed, we will do a Docker build to generate a container that will run that has the output of the .NET build within inside of it. We're then going to create a network. I'm calling it step 11 rather than called Web and SQL in this instance. We're then starting up a container on line 19. I'm specifying that the container it's going to live inside of is called step 11. It's going to be bound to port 1337, which is going to go through to port 80. So the ASP.NET application, and then the SQL server is also within inside of that network. So this time I've actually just put them both within inside of the same network. So let's run that. And we wait for the .NET compile to take hold. Luckily, it's a very simple application, so it doesn't actually take too long to run. That's starting up. We're starting to build the Docker image based off of that, so we see all of our layers getting executed. We're creating our network. We're starting our containers. If we do Docker PS, see that I have the SQL server and we have the .NET demo application. If I open up a browser, oops. Realize I didn't close my tabs. Open up my browser again. And then we go to localhost 1337. So it's hello world ASP.NET application. I want to register an account. We'll give it that, and we'll give it a password. And we'll hit register. But we haven't actually created the database yet. But this has obviously worked that out. Like, it's obviously been able to talk to the database and gone, well, the database that you're trying to access doesn't exist. But because I'm running this in development mode in my container, I can use the EF migrations. I can apply those migrations. And I should have left link pad running. There we go. If we have a look here, migrations should be done by now. There we go. Now we've got a database. It's got tables within inside of it. If I just reload this page, resubmit that form, I'm now successfully logged in. So my web application and my SQL server, they're able to talk to each other. I'm able to create stuff in those two environments. Excellent. So let's just go up and stop those, clean everything up. And then we're going to go to our next one, because I'm drastically running out of time. We've got a couple more demos to go. All right, so I was running my SQL server and my web server in the same network. But realistically, you probably want to have some kind of network isolation between them. We probably don't even want our SQL server externally accessible. From a production standpoint, we want to block all incoming traffic to that SQL server, just to reduce one of the attack vectors. So to do that, we can create them into separate networks, and we don't actually have to do any public port bindings. So in this case, I'm creating two networks, step 12 _web and _SQL. Excuse me. The web application will live in the web network. The SQL database will live in the SQL network. But I'm then going to, here on line 24, I'm going to connect the SQL network to the web container. So, so how that looks then, if we run, we'll come back up here, and if we do, give that a moment. Forgot it actually has to rebuild the application again because my script wasn't smart enough to see if there was a previously done build output. Everything's up and running. Now we have the containers up and running, so we can do docker ps. We see that they're both there. Now you'll see that the SQL server, it's bound on port 1433, but only internally. It doesn't have a host port binding like the one below it. You see 0000 local port forwarding through to port 80. I don't have a local host port binding to that. So inside of linkpad, if I was to refresh my connection to the database, it's going to time out because I have no ability to access that that container. Sorry, not that container. Yeah, I have no access to that SQL server. But my website, if we come back to localhost 30, there we go to that one. Give it a moment. Register with a password. Whoops. So my web server is still able to talk to it because they're in the same network. It's been connected to the SQL server's network. That SQL server is exposing itself on port 1433 on its own network, but not to its host. So this is how you can do network separation and isolation. So I can have that set there and kind of use fairly standard DMZ sort of setup that you might have in production. Sounds like someone else has finished, which means that I have only a few minutes left to go and 2 more demos. So let's jump forward to step 13. Now I said at the start, I had a joke in the title, which is that this is Docker from scratch. And the reason that I say from scratch is the most primitive image that you can create a container from. It's technically not an image, like you can't actually pull it down from a container registry, but you can still build something from it. Scratch has nothing installed in it by default. Where we used Ubuntu previously, and I was able to connect into and do using bash, and then I could execute commands against it. It's got a few other primitive things in there. It's got like apt if you want to be able to install some additional software into your container. Scratch doesn't have that. It doesn't even have SH. So you cannot, like, you can create an interactive container of Scratch, but you can't connect into it because it's got no processes within inside of it to run. So I want to show you how you can use Scratch. So I want to create a really simple binary that I can chuck into a Scratch container. So I've done that with Go. Go is the easiest one easiest language I know to create just a native binary that I can execute. I have a super complex Go application here, which just says hello world. I use Docker run to do a build in a Golang container, which is what I'm doing up on line 5. That will output me a binary, and then I will build using the Docker file. I will run that container, and that that container that's from Scratch, the only thing it will have inside of it is the output of the Go build. So let's run that. So it's going super fast, and then I've got to clean up afterwards. Let me actually just remove the, oops. Get rid of that line. We'll just run it again. I just kind of want to show you how this looks. So if I do Docker images, so we have this DFS-scratch, 1.5 meg. That's how big that image is. So it can be really highly performant to use Scratch in a production scenario because it's tiny and you can run a lot of these in parallel then. Let's just undo my changes, and then let's go to our final demo with 3 minutes to spare. I actually added this final demo since I've done the last time I've done the talk, so I wasn't sure I was going to get to it. But something that's fairly recent to Docker, kind of the last sort of 6 months, I think it was, they added this ability to do what they call multi-stage Docker files. So a Docker file, traditionally, you could have one from directive at the top, and then you would have a bunch of stuff, and that would produce you an image at the end. So if you wanted to use, do like a CI/CD process, like ASP.NET Core does when you're using Docker files in that, you do build in one, you take the output of that, and you push it into another another image. And we were doing that with our Golang. We were building in one, we were pushing that build output to our Scratch. Well, with a multi-stage Docker file, I could have all of those in the single file, and I'll get an image that is using the very final from directive as where we're starting. So now I start with from Golang 1.8, and I'm saying as build. So this is going to be the build image. Set a working directory, copy in some files, execute the Go build, and then I'm able to, here on line 11, I'm able to copy files from a previously created container into this new container that's running to produce my final image. And that can be really powerful if you've got, like, you want build output that you can just move across, or you want something that happens inside of one container that never ends up on the file system of the host. You can do some really good isolation in that. And this works exactly the same as the other one. We just have our builds. We have a slightly different bit of an output because we have these 2 containers. And then I've done a whole bunch of delete and clean up. And that one, I used a total of 3 meg to run those 2 Docker files side by side. All right. So with 1 minute to spare, when my slides do pop back up, Scratch, from Scratch, where we started this talk, it's not particularly useful because it's actually really hard to use as just a baseline image, but it can be used for really high-performant containers that you want to run. Images are great for experimenting. Pull it down, play around with the container that's running off an image of a language you want to experiment with, an application that you wanted to test and stuff like that, and then destroy it at the end, and you don't have to worry about polluting your local file system. Compose is a great way to represent environments, but you can actually just do that all via the standard commands. And it's good to understand that what the compose file actually finally represents. Thank you. Unfortunately, I think we're out of time for questions, but I'll be around if you want to ask anything. But thanks for attending.